So in this video, we're going to start talking about the concept of continuity. So continuity is a very important property of functions in mathematics, and particularly in calculus, it is needed for a lot of the really important theorems. And if functions are not continuous, then things become a lot more difficult. So we generally like continuous functions. They generally make the math a lot easier. So we need a way to verify if a function is continuous. We need a definition of continuous. So I feel like we've kind of explored the concept a little bit already. So in general, the kind of easy definition of continuity is that a function is continuous if you can draw it without lifting up your pen. Okay. In other words, there's no gaps in the function, right? You don't have to leave any open circles anywhere. You don't have to move up to a different point, things like that. So let's just briefly look at a couple of graphical examples here. So something, for example, like a line x minus 1, for example, is clearly going to be a continuous function. And just using the easy definition of continuity, we'll write down a more rigorous definition in a minute. But we can see that this function is something that we can draw without lifting up our pen, right? There's no gaps in it. There's no jumps, nothing like that. Something like x squared, same idea. It looks very different, but it also is just a continuous line, right? Or a continuous curve in this case. Okay. In general, polynomials are continuous. So if we look at something like the absolute value of x minus 1, well, that function by itself is continuous, but now I want to divide by x minus 1. Now this green line here, we see an example of something that's not continuous. I'll go ahead and turn these ones off so we can just look at this one. We can see that if we just look at the part to the left of 1, where x is less than 1, it looks continuous on that part. And if we look to the part where x is greater than 1, to the right of 1, then the function looks continuous on that part. But it's this point at 1 where we have the issue, right? The function is not even defined at that point, and it is jumping between the points. Okay. So those are both going to be issues, the function being undefined at that point and the function jumping at that point. In other words, the left hand and the right hand limits are not the same. So these are kind of the three things that we're going to need for the function to be continuous. We're going to need one of the things is that we're going to need the function to be defined at that point. If it's not defined at that point, how could it be continuous at that point? There's going to be some gap there because there's no point there. We're going to need the limit to exist at that point, right? In cases where the limit doesn't exist, we can see the function. The reason the limit doesn't exist here is because it's going different places. So again, that's kind of opposing our view of continuity. And the third thing we're going to need is that that limit and that output are going to need to be the same thing. Okay. So that third condition is the big one and kind of can summarize the entire thing. So let's look at a graphical example of one of those. Okay, so this one, we have the function x squared minus 1 divided by x minus 1. So if we went ahead and canceled this out, we would see that it looks like the function x plus 1. But the difference, so it looks like the line x plus 1, but the difference is that at this point, at x equals 1, this function is undefined, right? So I put the open circle at that point there, so it's easier to see. And then the function also has this point at 1, 4, so the function is not actually undefined at this point. The way we would write this is as a piecewise function, so I can't write it all out on the graph screen here. So let's go ahead and move back to this screen. So this is going to be the function that we're looking at graphically then is f of x equals x squared minus 1 over x minus 1 if x does not equal 1, and it equals 4 if x equals 1. Okay. So we can see that the function's clearly not continuous, specifically at this one specific point, right? It has this jump up to this point and then this jump immediately back down to continue on the line. So if we look at this mathematically, what's happening here is that f of 1 is equal to 4, but the limit as x approaches 1 of f of x is equal, well, we could just look at the graph real quick. It looks like it's equal to 2, right? And this is not equal to 4, which is the output of the function. So this is how we will define continuity, okay? That the limit needs to exist at that point, the output needs to exist at that point, and they need to be the same number. So another thing you might notice is that this is only defining continuity at a single point, right? This is talking about whether a function is continuous at the point 1 or if the function is discontinuous at the point 1. So if a function is continuous at every point, then we say the function is continuous. Generally, with the functions we're going to be looking at, there's only a couple of points in question about whether or not they're continuous at those points. So in general, we're just going to be showing that a function is continuous at a single point. And then usually, if it is, it'll be clear that the rest of the function is continuous everywhere else. Namely, a lot of the special functions that we've been looking at are continuous at most points, with the exception being rational functions, the logarithm functions, right, where it's not defined at 0. So some of the special cases like that. So let's go ahead and write this as a definition then. So the definition for continuity, a function f of x is continuous at a point A if and only if the following 3 conditions are satisfied. And these are what we just saw. 1, f of a is defined. Can't be continuous there if it's undefined there. 2, the limit as x approaches a of f of x exists. Remember, this excludes where the limit is infinity. If the limit is equal to infinity, we might write down that it's equal to infinity, but that still technically means it doesn't exist because limits need to be real numbers. And 3, this one can kind of summarize the whole thing. The limit as x approaches a of f of x is equal to f of a, right? And clearly they can't be equal if one of them is undefined or doesn't exist. So we really only are going to be looking, we only really need to look at the third one, unless it's clear the function, doesn't satisfy one of the first two, right? So again, this is only at a point A, right? So this is not looking at if the function overall is continuous. Let's go ahead and just look at a couple examples. Okay, so f of x equals 1 over x. Okay, so this function is not defined at 0. F of 0 is undefined. Okay, so by condition 1, we say f is, you could say discontinuous or just not continuous. We don't really use the word discontinuous. We use the word discontinuity, but I think it's more natural to say is not continuous here. It would be natural to say f has a discontinuity at 0, and we'll look at different types of discontinuities. Okay. So here, this is failing step 1, so there's no need to check the other ones, but we could, of course, the limit as x approaches 0 of f of x in this case also does not exist. It's going to infinity on the right side and negative infinity on the left side. Okay. So let's go ahead and look at a piecewise function example. So these are always interesting because it's natural that a lot of piecewise functions, they have some kind of gap in them, but they don't necessarily have to, right? They can be connected at that point. Without graphing it, we can't really tell. Okay, so this is the function in question here. So let's let f of x equal negative x squared plus 4 if x is less than or equal to 3, and 4x minus 8 if x is greater than 3. Okay, so we'll go ahead and graph it first, though generally we're going to want to do these ones without graphs, but let's just look at it. So negative x squared plus 4 is the first function, and it's only defined to the left of 3. I won't cut it off on here. We can just kind of visualize. Okay. So at x equals 3 is where the switch point comes, right? So that's right here. So we can see that to the left of 3, we have the purple line. And then to the right of 3, we have the white line here. So it's clearly not going to be continuous, right? If the function cut off at 2, if that's where it switched, then this would probably be continuous. But because it's cutting off at 3, I just realized you can't see this function at 3 on the video here, so it's down here, right? This is not going to be continuous. Okay, so let's go ahead and show that mathematically. So first, for condition 1, I don't think we necessarily need to show that. We don't necessarily need to show all 3 conditions. We just need to show that the limit and the output are the same. So we'll go ahead and find the output, and then we'll go ahead and find the limit. So f of 3, and hopefully it's clear that the point in question is at 3, right? We're only looking for continuity at 3. We know the function negative x squared plus 4 is generally continuous, and that the function 4x minus 8 is generally continuous. They're both polynomials. Polynomials in general are continuous. Okay, so maybe I'll write that as a like theorem or something in a second here, just so that we kind of have that to reference. But the only point in question here of where it would not be continuous is at that point where we change to different parts, right? So on the left of 3, we're looking at the negative x squared plus 4 part. And then to the right of 3, we're looking at the 4x minus 8 part. So just at that transition point. So f of 3 is equal to, that's going to be working off the top part here. So negative 3 squared plus 4. The negative is not being squared. So this is going to be negative 9 plus 4, which is negative 5. And now this one is probably helpful to look at the left and right side limits. Okay, so the limit as x approaches 3 from the left of f of x, that's going to be working off the top part of this graph. So that's going to be the same as the output here. But the limit as x approaches 3 from the right of f of x, that's coming in from this side, right? So we're working off of this part of the function. So with the direct substitution on that side, we get 12 minus 8 is equal to 4. So actually, this is really failing condition 2, which is that the limit actually doesn't exist at all, right? The left-hand limit and the function are the same. So we can say that this function is left continuous. We do have this notion of one-sided continuity as well, which we'll explore later. But for now, just looking at it overall, we say that the function is not continuous. Okay, so real quick, just to write down as a theorem, polynomials and rational functions are continuous At this point, you might be wondering why rational functions are included in this, right? Because they clearly are not continuous at certain points. So they are continuous at every point in their domains. Okay, so that's the key here. If the function is in the domain of a polynomial or a rational function, then it is continuous at that point. Rational functions are made up of polynomials. It's a polynomial divided by a polynomial. So it'll naturally extend to rational functions, but specifically at the points in their domains. So polynomials have a domain of negative infinity to infinity. So polynomials will be continuous at every point. Rational functions, of course, will not be. They tend to have, of course, they have denominators. So they tend to have a point at which they are not continuous, right? But they will be continuous at every other point. So again, just looking f of x equals 1 over x, this function is not continuous at 0, but it is continuous at every other point. And you could show that mathematically.